This is the Unit 3 practice exam for Math 1050 Spring 2022. Question number 1, graphing this is graphing an exponential function. This is section 4.1. The way it was laid out in instruction was basically 3 steps. Step 1 is to locate the horizontal asymptote. Now you see there's a -1 right here outside the function. That's going to move the horizontal asymptote down 1 unit. Normally it's right here at y equals 0, so this -1 is going to move the horizontal asymptote down 1 unit. To y equals -1. Okay, next we need, pretty much the whole next step is locating a few additional points. We need a total of 3 points. One of those needs to be the y-intercept. You find the y-intercept by letting x equal 0. So if you plug a 0 in for x, 3 to the 0 power is 1. 1 subtract 1 is 0. So 0, 0 is on the graph. Now we can let x equal whatever value we want at this point, because if you recall, the domain of exponential functions is all real numbers. So 1, for example, if we plug in a 1 for x, 3 to the first power is 3. 3 subtract 1 is 2. So 1, 2. And then if we let x equal 2, and then plug in a 2 for x, 3 to the second power is 9. 9 subtract 1 is 8. So 2, 8 is on the graph. And there you go. The second part of this, state the domain and the range. Domain, as you can see, the graph reaches -infinity to the left, and on the right is going to eventually reach positive infinity on the x-axis. So the domain is all real numbers, or -infinity to positive infinity. The range, remember the range has to do with the y-axis, it goes as low as approaching this horizontal asymptote. Now the horizontal asymptote is at -1. So the lowest value in y on this graph is it approaches -1 but never actually reaches -1. So we put a parenthesis around -1, and then on the y-axis it's going to go as high as positive infinity. Question 2 is from section 4.3, graphing logarithmic functions. Very similar in how we graphed exponential functions, but logarithm, remember, is the inverse of an exponential. So with exponential functions, recall the first thing we did was locate the horizontal asymptote. So for logarithmic functions, the first thing we would do is locate the vertical asymptote. Normally it's right here on the x-axis, or sorry, on the y-axis at x equals 0. However, here x minus 2 is a translation to the right 2 units. So that's going to move the vertical asymptote to the right 2 units, to x equals 2. So there's a vertical asymptote. Now, as with exponential functions, we needed a few additional points. We need the same thing with logarithmic functions. We need a few additional points. One of those points, it's nice if we can locate the x-intercept where it crosses through the x-axis. That means we need a y value of 0. So I plug in a 0 for y. Remember, f of x is the same as y. We would solve an equation 0 equals log base 3 of x minus 2 plus 1. Now we need to solve for x. X minus 2 is inside of a logarithm, so we can't get to x minus 2 until we can get rid of this logarithm. Now we can't cancel out a logarithm until that logarithmic expression is the only thing on that side of the equation. So this plus 1 needs to move over here as a -1. So subtract 1 on both sides. Now we can use a base of 3 to cancel the logarithmic function. So now we have 3 to the -1, which is 1/3, equals x minus 2. If you add 2 to both sides, x equals 2 plus 1/3. So if we have 2 plus 1/3, it's the same as 6/3 plus 1/3, which is 7/3, or 2 1/3. So that's about right here, 2 1/3. Now you can continue to plug in y values and substitute those y values in right here for f of x, and then follow the same procedure here. You can also, if you're careful, remember we talked about this in class, if you're careful you can choose x values. When I say if you're careful, remember this is a log base 3. So whatever this expression turns out to be, x minus 2, that needs to be a power of 3. For example, if we plug in x equals 5, 5 subtract 2 is 3, and 3 obviously is a power of 3. So 5 would be a good choice to plug in for x. Again, 5 subtract 2 is 3. The log base 3 of 3, let me write this down. Log base 3 of 3, 3 is to the raised to the first power, so the 3's would cancel, leaving a 1. So the log base 3 of 3 is 1. 1 plus 1 is 2. So 5 comma 2 is on our graph. We could also plug in 3, not because 3 itself for x is a power of 3, but if you recall, 3 subtract 2 is 1, and it doesn't matter what the base of the logarithm is. Anytime you have a log of 1, that's always 0, and then 0 plus 1 obviously is 1. So 3 comma 1 is a point on the graph. So we have our graph. Now it also asks for domain and range. Domain now has to do with where this vertical asymptote is. There are no x values to the left of that vertical asymptote, so all of our x values are starting to the right of this vertical asymptote. Now there are no x values directly on this line of x equals 2. This line is getting close, the graph is getting closer and closer to this vertical line of x equals 2. So the domain will start at 2, but we're not going to include it. We're going to put a parenthesis around it. So from 2 to infinity. Range, this graph is going to continue in this downward direction. So on the y-axis, we're going to go all the way down to negative infinity. And it will continue to go up and up and up in the positive direction on the y-axis. So the range is all real numbers, or negative infinity to infinity. Okay, question 3 is from section 4.3, simplifying logarithmic expressions using properties of logarithms. Now, if you look here, these are all log base 10. These are common log. So log 25 or log 2, log 5, these, we don't have matching bases, and we can't change 25 into something raised to the 10 raised to some power. So the key here is that we combine using the properties of logarithms we learned about in section 4.4. This one would be the product property. So log of 25 times 2 is log 50. Remember the product property, it says if you have two logarithms separated by a plus sign, you can condense them into one logarithm by multiplying the terms inside of those logarithms. 25 times 2 is 50. Now we have the quotient property that says if you're subtracting two logarithms that have the same base, these are both log base 10, you can condense those into a single logarithm by dividing the terms inside. So this would be 50 divided by 5, which is 10. So now we have log 10, and remember common log that has no base is just log base 10. This 10 is raised to the first power, so those cancel out. So the answer is 1, leaving, and the reason the answer is 1 is that's the exponent that's left over when you cancel this base with that logarithm. Now, part B, a base of 7 is the inverse of a log base 7, but this negative 2 is in the way. So if this negative 2 were gone, then 7 as a base would cancel the log base 7. So we have to apply one of those properties again from 4.4, the power property. If you recall, if there's an exponent on an expression that's inside of a logarithm, you can move that exponent down in front. Well, that property also works backwards. If you remember, you can take the coefficient here and move that coefficient back up as an exponent. So this will be 7 to the log base 7 of 3 to the negative 2. Now that we have a base of 7 and the log base 7 has no more coefficient, those act as inverse operations and cancel each other out. The log base 7 and the base of 7 cancel, leaving just 3 to the negative 2 power, which is 1 over 3 squared, which is 1/9. Okay, part C, if you recall, I mentioned this a couple of times. Logarithms and radical signs don't mix well. So the first thing I would do here is change this to 8 to the 1/2, 8 to the power of 1/2. And then we can apply the power property that we spoke about in this problem here. If you have a base here that doesn't match the base of the logarithm, you can move the exponent down in front. And then I'm going to change 8 into a power of 2. 8 is 2 raised to the 3rd power. So this is 1/2 log base 2. And then instead of 8, I'm going to write that as 2 cubed. Now the log base 2 is going to cancel with that base 2. And now we have 1/2 times this 3. This 3 is no longer an exponent because there's no base that it's attached to. So the 3 just becomes a numerical value multiplied by 1/2, and then 3 times 1/2 is 3/2. Question 4 is from section 4.4. Expand this logarithmic expression into multiple logarithms. So first thing to notice here is there's an exponent on the outside of this expression. So there's a couple ways we could proceed. We could evaluate this exponent into the parenthesis, or we can just apply the power property that says this exponent that's on the outside can move to the front and become a coefficient. I'm going to do it that way. So I'm going to move that 3 down in front and make it a coefficient. Now I've got the product of x squared times y. So I'm going to apply the product property and separate this into 2 logarithms. And each logarithm is going to have this same coefficient of 3. So this is 3 times the log base 2 of x squared plus 3 times the log base 2 of y. Now this expression here has an exponent, so that's also going to move down in front and multiply the 3. So that's going to become 6 times the log base 2 of x plus 3 times the log base 2 of y. Okay. Question 5, we are going to invest $10,000. We want the money to double in 30 years. What would the interest rate need to be if it's compounding continuously? So the continuously compounding formula is right there. Now, remember, P is the principal investment. That's what's initially invested. That's $10,000. A is the future amount after so many years T. The future amount is we want our money to double. So the future amount is going to be $20,000. And we want that to double in 30 years' time. So T is 30. The question is, what would the interest rate need to be? So we're solving for R. So the future amount is $20,000. The principal investment is $10,000. Time is 30 years. We need to solve for R. So using the formula, 20,000 for A equals 10,000 for P. Now we need to solve for R. R is the variable and it's an exponent. And we can't solve for a variable if it's an exponent. So we need to use logarithms. This is an exponential equation. The way that we solve exponential equations is to use a logarithm. Now the logarithm that's going to cancel a base E, remember, is natural log. But the first step is to isolate the exponential term. The exponential term is the base combined with the exponent. We need to get rid of the coefficient. So if you divide the 10,000 to both sides, you're going to get 2 equals E to the 30R. Now we can use natural log on both sides. Natural log cancels the base e. So we have the natural log of 2 equals 30 times r. If we divide by 30, then we have r is equal to the natural log of 2 divided by 30. And this is where you would get your calculator out. And your scientific calculator does have a natural log button. So if you type in natural log of 2 and then divide that by 30, you're going to get 0.023. So if we convert that back into a decimal, or sorry, if we convert that back into a percent, that would be 2.3. That would be our interest rate. Okay, question 6 is from section 4.5, solving exponential equations, which we pretty much just did here in question 5. It's going to be a very similar thing we're doing here in question 6. So we need to isolate the exponential term and then cancel the base using a logarithm. Now, the exponential term is here, so we have to move the 3 over by adding. Now we can use log base 2 on both sides, because that'll cancel the base. So we have 3x minus 1 is no longer an exponent because the base 2 has been canceled. So we can add 1. And remember, we can't add or subtract anything from the numerical value inside of a logarithm. So the plus 1 is considered outside the function. So now we have log base 2 of 27 plus 1 equals 3x. So we can divide by 3 and divide by 3. So the exact value for x is log base 2 of 27 plus 1 divided by 3. That's the exact value. It also wants the approximate solution. Remember, the scientific calculator cannot do log base 2. So here you have to employ what we call the change of base formula. So if you wanted to see what that looks like written out, it would be log 27 divided by log 2, and then we would add 1 to that, and then we would divide by 3. And this calculation here can be done on a calculator because these are now just common log. So on a calculator, you would type log 27, and then you would divide that by log 2, then you would add 1, then divide by 3, and you'd get 1.92 as an approximate value for x. Now, part B, also exponential equation. You can tell because we have a base and an exponent, and the variable is in the exponent. The base is e to the 0.1x. Remember, 2 in this case is a coefficient. So when you get rid of this 2, we got to get rid of this 9 in order to isolate the base. So subtract 9 as a first step. Then divide by negative 2. Now use natural log to cancel the base e. And what we have is 0.1x equals the natural log of 4. And we can divide by 0.1 to isolate x. So there's the exact form. And the approximate form would be 13.86. Now, question 7, this is also from section 4.5. Now we're solving a logarithmic equation. Step 1 is to isolate the logarithmic term. That includes the logarithm combined with the expression inside the logarithm. So if there were a coefficient in front or something outside the logarithm, adding or subtracting, we would move that to the other side before we cancel the logarithm. Now there's nothing in front, nothing outside, so the logarithm is already isolated. So we can move on to step 2, which, if you recall, you cancel a logarithm by using a base. In this case, we use a base 3 because this logarithm has a base 3. So that's called exponentiating. If you use a base of 3 on both sides, then the base of 3 and the logarithm cancel, and then 3 to the 4th power is 81. Add 1 on both sides, and then divide by 2 to get x equals 41. Now part B, talked about this a few times in class. First, recognize what kind of logarithms we're dealing with. These are all base 10 logarithms, or common log. The base that we're going to use to cancel these logarithms is a base 10. Now, the common mistake that I've showed you a couple times is you cannot use two bases on the same side of the equation like that to cancel logarithms. This is not going to work. You can use one base on the left side of an equation and one base on the right. It has to be the same base. You can use a base on each side of a logarithmic equation. So that's not going to work. You can't cancel all the logarithms straight away. You've got to combine those two logarithms into one logarithmic expression. And the reason we can do this is there's a plus sign, and both of these logs have the same base. This is the product property that we talked about in section 4.4, condensing two logarithms into one logarithm. And the expression here and here are going to multiply. So x minus 3 times x plus 2. Now that we have one single logarithm here and one single logarithm here that have the same base, base 10, now we can use a base of 10 on both sides to cancel each logarithm. And we have x minus 3 times x plus 2 equals 4x. So now we are no longer solving a logarithmic equation, even though that's what we set out to do. At this point of the process, we're solving a different kind of equation, and you might wonder, well, what kind of equation is this? If you were to multiply these two binomials together, you would have x squared minus x minus 6 equals 4x. And now hopefully it's more apparent. This is a quadratic equation that we're going to solve. And you know several techniques, or you've been taught several techniques of how to solve a quadratic equation: factoring, quadratic formula, completing the square. We do have to have this side equal to 0. So we've got to move the 4x over by subtracting. If you subtract 4x on both sides, you're going to get negative 5x minus 6 equals 0. Now you consider the expression here, and if it does not factor, you have to use the quadratic formula. This one does factor into x minus 6 and x plus 1. Then from each factor we can get two separate possible solutions, x equals 6 and x equals negative 1. And I say possible solutions, the thing you need to keep in mind when you are solving logarithmic equations is you cannot have any value for your variable that is going to turn the expression inside of a logarithm negative. Remember that you can't take the logarithm of a negative number. Negative 1, for example. If you plug negative 1 in here, for this x, negative 1 plus 2 is 1. So it's fine here, but if you plug it in here, negative 1 subtract 3 is negative 4. Log negative 4 is undefined, as is right here. Log 4 times negative 1 would be negative 4. Log negative 4 is undefined. So x equals negative 1 is what we called in class an extraneous solution. It's a solution that's outside the domain for this function. X equals 6 doesn't necessarily mean it automatically works, so we still need to consider here 4 times 6 is 24, that's okay. 6 plus 2 is 8, that's fine. 6 minus 3 is 3. Those are all positive values, so x equals 6 is okay. Question 8 is from section 4.6. The question here is, well, there's two parts to this. We first need to find a function that models the amount of bacteria at any time, and then we need to use that model to find the number of bacteria after 10 hours. So two parts. So first, let's find the function that models this exponential growth situation. If we start with 3,000 cells and it doubles every 40 minutes, the count here doubles. This keyword doubles. In your notes from section 4.6, hopefully you have a model for exponential growth that specifically addresses when you have doubling time. That's why I use a base of 2, because the quantity is going to double every so often. And then the exponent is t for time, and then the variable x here just represents the doubling time. And remember, a sub naught is your initial count. So 3,000 is going to go in place of a sub naught. Your doubling time is going to go in place of x, and that's your model. The amount at any time t is equal to 3,000 times a base of 2 raised to a power of t divided by 40. So that answers this part of this question. Find a function that models the amount of bacteria at any time t. That's right here. Now we need to use the model to find the number of bacteria after 10 hours. Now 10 hours is a measurement of time. Measurements of time go in place of t. However, our doubling time is in terms of minutes. It doubles every 40 minutes. So whatever value we place in for t also has to be the same unit of measure or unit of time as our doubling time. So 10 hours is 600 minutes. So 600 minutes is what's going to go in place of t. So the amount of bacteria after 600 minutes is equal to 3,000 times 2 raised to a power of 600 divided by 40. And then at this point, you would plug it into your calculator to find the approximate count after 600 minutes. And I'm getting 98,304,000 bacteria. Okay, this is also from section 4.6. We need to know how long it's going to take for the fish population to reach 5,000. So here's the model that models the amount of fish at any time t. 5,000 is a measurement of population, so that's going to go in place of p of t. And the question is, how long will it take? That means solve for t. When p of t, the population, equals 5,000. So we replace p of t with 5,000. And solve for t. Now, ultimately, what we have here is an exponential equation because we have a base with an exponent that has a variable in it. So eventually, we're going to get down to just e to this power so we can use natural log. So we got to get rid of everything around this exponential term so that we can use logarithm. Now, we have a fraction here. We've talked about this many times. We don't like to solve equations with fractions. So I'm going to multiply both sides by the denominator to cancel it out. And now I've got this is equal to 10,000. So I can also divide by the 5,000 here. Rather than distributing it, I can just divide by 5,000. That's going to give me on the right side 2. Now I can subtract 1. And then divide by 19. Because again, what I'm trying to get is the base and the exponent. This is the exponential term. I'm trying to get this all by itself so I can use a logarithm. Now I finally have this exponential term isolated, so I can use a natural log to cancel the base e. So now the negative 1.56t is no longer an exponent because the base e is gone. So the negative 1.56 is just a coefficient that can be divided over here to isolate t. So the amount of time in years is natural log of 1/19th divided by negative 1.56. So we want to approximate this on a calculator. And I'm getting 1.89 years. Now we begin starting in question 10. These are questions now that come from chapter 8, sequences in series. So 10, part A and B, are from section 8.1. And I have two instances here of two types of formulas to represent a sequence. Here is what was called an explicit formula, if you look in your notes for 8.1. And this is a recursive formula. And all you're doing is the first four terms of each sequence. Now what's important here is you recognize what kind of formula is which. Down here, the recursive formula is recognized because A gives you the first term, and B, the nth term refers to a previous term, n minus 1. That's a key characteristic of a recursive formula. You have the first term, and then the nth term refers to the term before it. Here, the nth term only refers to n, and n only. And remember, n represents a spot in the sequence. So for an explicit formula like this, in order to find the first four terms, you need to plug in n equals 1, and then n equals 2, and then n equals 3. So let's start with part A. To find the first term, again, the first term is when n equals 1. So if you plug in a 1 right here, for n, 1 subtract 1 is 0, 2 to the 0 power is 1, 1 times 2 is 2. So the first term is 2. Now for the second term, I'd plug in a 2 for n. 2 subtract 1 is 1, 2 to the first power is 2, 2 times 2 is 4. For the third term, n equals 3, 3 minus 1 is 2, 2 squared is 4, 4 times 2 is 8. And for the fourth term, 4 subtract 1 is 3, 2 to the third power is 8, 8 times 2 is 16. That's how you find the terms with an explicit formula. You plug in for whichever term you're trying to find. If I wanted to find the 10th term over here, I'd plug in a 10. Now, a recursive formula, and again, you recognize a recursive formula on two characteristics. You're given the first term, and then the nth term refers to a previous term. So we already know the first term. It says right here, the first term is 2. Now what we're looking for here is the second term, okay, or a sub 2. Now one way you could think about this is if you're trying to find the second term a sub 2, or when n equals 2, you could plug in 2 right here, a sub 2. That just means you're finding the second term. So let me write this. A sub 2 means you're finding the second term. Here you'd plug in a 2. And a sub 2 minus 1, this becomes the second term is equal to a sub 1, which is the first term, plus 5. Well, the second term then is equal to the first term plus 5. First term is 2. 2 plus 5 is 7. Now, what we're searching for is the third term. The next term here is the third term, right here. This is when n equals 3, or the a sub 3 term. So if I want to find the a sub 3 term there, I can imagine there's a 3 right there. 3 minus 1 is 2. So what this is saying is that the third term, a sub 3, is equal to this turns into a 2, remember, so that's a sub 2, which is the second term, plus 5. So any term is equal to the term before it, plus 5. So you're always just adding plus 5 to the next, to get to the next term. So 5 added to 7 is 12. And then the fourth term is going to equal the third term, plus 5. Well, the third term is 12. 12 plus 5 is 17, and so on and so on. So this recursive formula really just says that any term is equal to the term in front of it plus 5. So this term is equal to the term in front of it plus 5. The next term here would be equal to the term in front of it plus 5. So 22, and then 27, and then 32, and then 37. We're just adding 5 every time. Now, for number 11, this is from 8.2 now, and that's not clear in the problem that it's from 8.2, but if you recognize what kind of sequence this is, from negative 11 to 19, you add 30, and then from 19 to 49, you add 30. From 49 to 79, you're adding 30. You're adding the same number every time, which makes this an arithmetic sequence, and that's what we studied in section 8.2. So what this really says is find the nth term, or the explicit formula, of this arithmetic sequence. So on the formula sheet that you'll see on the exam, one way you could do this is to use the nth term of an arithmetic sequence, which is first term plus n minus 1 multiplied by the common difference. Well, the first term is negative 11, and then the common difference is what's being added every time. So if we wanted to plug that information into this formula and then distribute, we get negative 41 plus 30n, and that's your nth term. You can do it that way using this formula right here. It's totally fine. The other way we describe this is an arithmetic sequence is described with an nth term formula that's linear, where you could think of this as a slope, a constant rate of change, which is plus 30 every time. That's a constant rate of change. And then negative 41, if we think of y equals mx plus b, b is your y-intercept when x equals 0, or an imaginary number in front of the first term when n equals 0. If we went 30 units in this direction, we would get negative 41 as a 0 term. And we know the common difference is 30, so we can, just with that information, use mx, or slope intercept form, 30n minus 41 from the 0 term, and we get the same nth term formula. Either way, you would need to give an answer that is the nth term. Whether you do it this way or use the 0 term with the common difference, it's up to you. Now, number 12, it is clearly stated that this is an arithmetic sequence. So we need to find the nth term. Again, you could use the nth term formula for an arithmetic sequence, first term plus n minus 1 multiplied by d. Now, we don't know what the common difference is, but again, relating an arithmetic sequence to a linear function. Linear functions have a slope. Slope is a constant rate of change, or the difference in y values divided by the difference in x values. So if we're thinking about this in terms of an input and output relationship with n and a sub n, the 15th term for n is equal to 53. And here the 33rd term, so n equals 33, is equal to 89. So here we can calculate a difference in y values, which would be 36. And here we could calculate a difference in x values, which would be 18. and then the difference in y divided by the difference in x, 36 divided by 18, means that the common difference is 2. And now that we know the common difference, we need to figure out what this first term is, a sub 1. Now, in this equation or formula, we know the common difference, it's 2. We don't know a sub 1, and right now a sub n and n are also variables. You can't solve an equation with 3 variables, you can only have 1 variable, and we want the variable, the unknown, to be a sub 1. That means we need to plug in something for n and something for a sub n that we already know. Well, we already know 2 of them. We know that when n is 15, a sub n is 53, or when n is 33, we know a sub n is 89. You can use either one of these 2 points here. So I'm going to use this top one, 15 and 53. 15 is which spot it occupies in the sequence, so that goes in place of n, and then 53 goes in place of a sub n, leaving a sub 1, or the first term, as the only unknown. And subtract 28 from both sides, and we get 25. First term is 25. So we can finish the nth term formula now, because the thing that we didn't know was this a sub 1. We knew that d was equal to 2. We just didn't know what a sub 1 is. Well, now we do. So the nth term is 25 plus n minus 1 times 2, and then we simplify that. To get our final version, 2n plus 23. That's never a bad idea to check. According to this, the 15th term should be 53. That should also be true in the nth term formula. If n is 15, 15 times 2 is 30. 30 plus 23 is 53. This should also be true when n is 33, so 33 times 2 is 66. 66 plus 23 is 89. So this formula does generate these 2 terms. So that would be the correct nth term formula. Didn't circle that. There we go. Now, question 13, evaluate the partial sum. On your formula sheet, you're going to have 2 partial sum formulas, one for the partial sum of an arithmetic series, and then a partial sum for a geometric series. And it's not clear, or at least it's not clearly stated, if this is an arithmetic series or a geometric series. So 38, 46, 54, 62, looks like we're increasing by 8 every time we're adding 8. If you're adding the same number every time or subtracting the same number every time, remember that's an arithmetic series. So the partial sum formula for an arithmetic series is n over 2 multiplied by the sum of the first term and the last term. Now we know the first term and we know the last term, so we know these 2 parts of this formula. What we don't know is n. Which term of the sequence is that? We know that this is the first term, this is the 4th term when n equals 4, but we don't know if that's n equals 10, we don't know if that's n equals 40. So we need to figure that out. Excuse me. So if we go back to something we know, like the nth term formula for an arithmetic sequence, which is the first term plus n minus 1 times the common difference. We know the common difference is 8. And if we plug 302 in for a sub n and solve for n, that's going to tell us which term of the sequence this is in. If we plug in an 8 for D and our first term as 38. So 302 as our A sub n term. First term is 38. We don't know the n value for that, but we know the common difference is 8. Now subtract 30 on both sides. So this would be 272 equals 8n. Divide by 8, and we get n equals 34, which means that this is the 34th term in this partial sum. So we no longer have a question mark there. We know that n equals 34, so we have the sum of the first 34 terms is 34 divided by 2, and then we add the first term to the last term. So 17 times, or multiplied by 340, which turns out to be 5,780. Part B is a different way of looking at a similar thing. Rather than writing out individual terms of the partial sum, the partial sum is represented using sigma notation. But again, you need to be able to recognize which partial sum, or even taking a step back, you need to be able to recognize that this is a partial sum. Remember, the sigma sign means summation, and since you're starting at 1 and ending at 13, you're only adding a finite amount, or a partial amount of a series, because a series goes on forever, but we're only taking the first 13 terms. So this is a partial sum, and then 6n minus 14 is linear in form. It resembles y equals mx plus b, which means this is arithmetic. So again, the arithmetic partial sum formula applies. Half of n multiplied by the sum of the first term and the last term. Now, n is pretty clear. We know that we're adding 13 terms. What we don't know is the first term here, or the last term, the 13th term. So that means all that means we've got to plug in 1 to find the first term, and then plug in 13 to find the 13th term. So when n equals 1, 6 times 1 is 6. 6 subtract 14 is negative 8. So the first term is negative 8. Now the 13th term would be 6 times 13, which is 78. And then 78 minus 14 is 64. So the 13th term is 64. So now the partial sum of the first 13 terms of this sequence becomes half of 13. And then the first term was negative 8. 13th term was 64. So we have half of 13 multiplied by 56. Half of 56 is 28, so this turns into 13 times 28, and that's equal to 364. Okay. Number 14 says find the nth term. So you're going to have to be able to recognize, first of all, what kind of sequence this is. Is this arithmetic or geometric? From 3 to 12, and then 12 to 48. 48 to 192, looks like we're multiplying by 4 every time. So if you're multiplying by the same value over and over again, that's geometric. On your formula sheet, it'll have the formula for a geometric sequence. Is first term multiplied by the common ratio raised to the power of n minus 1. Here the common ratio is 4. First term obviously is negative 3. That's all you need. To write the nth term is first term multiplied by the common ratio raised to a power of n minus 1. Now, 15, evaluate the sum of the following geometric series. So this is a partial sum because it has a beginning value and an ending value. So we need to use the partial sum formula for a geometric series. So what we need to know here is first term, a sub 1, which we know. We need to know the common ratio. So from 1 to 4 to 16 to 64, looks like we're multiplying by 4 every time. So the common ratio, so first term a sub 1 is 1, common ratio is 4. So we know r. What we don't know is n. N is the number of terms that are being added. 65,536, we don't know if that's the 10th term, the 40th term. We don't know. So we need to use the nth term formula, kind of like we did in a problem previous, to figure out what spot of the sequence this value occupies. So we need to write the nth term. So a sub n is equal to the first term, 1, multiplied by common ratio 4 raised to the power of n minus 1. Now this is an a sub n value, so that can go in place of a sub n, and then we'll solve for n, which will tell us what spot in the sequence that is. So 65,536 equals 4 to the power of n minus 1. Now this is an exponential equation to solve. So what we need to do is cancel this base so that we can get n minus 1 to not be an exponent. So we all know by now what cancels a base is a logarithm. So we're going to use a logarithm on both sides. I'm going to use a log base 4 here and a log base 4 there, because a log base 4 cancels the exponential base 4. So we have now this equation to solve. So if we add 1, n is log base 4 of 65,536 plus 1. Now we need to figure out the exact value of this. Can't do log base 4 in a calculator, so we need to change that using the change of base. So log base 10 now of 65,536 divided by log 4, and then we add 1 to that. And that'll give us the value of n. So it turns out the log base 10 of 65,536 divided by the log base 10 of 4 is 8, and then 8 plus 1 is 9. So this term right here is when n equals 9, so that's the 9th term. So we can use the all the information now for this formula. The first term is 1, r is 4, that's raised to the 9th power, and then divided by 1 minus 4. So the sum is equal to 1 times 1 minus 4 to the 9th divided by 1 minus 4. And again, at this point, definitely a calculator problem. It turns out to be 87,381. And part B, again, is clear that this is a partial sum because we have a starting value of I and an ending value of I. We're only adding 8 terms of the series, which is a part of the series, so it's a partial sum. And then this formula is written in exponential form, making it a geometric. This is the nth term formula for your geometric sequence. So we're going to use this same formula for the partial sum of a geometric series. So the sum is equal to first term times 1 minus r to the n divided by 1 minus r. R, the common ratio, is 3. Okay, the number of terms we're adding together is 8. And then the first term, if we plug in a 1 for I, 1 subtract 1 is 0. 3 to the 0 power is 1. 1 times negative 2 is negative 2. So the first term is negative 2. So we can plug all of that information into the formula and run it through the calculator. And we get negative 6,560. Now part C is an infinite sum. So there is conditions now. There are conditions that need to be met. First of all, to have an infinite sum, it needs to be geometric, and this is the nth term formula of a geometric series. And then the common ratio needs to be less than 1. 1/2 is less than 1. So the formula for an infinite sum of a geometric series will work. We just need to know the first term and then the common ratio. Well, we already know the common ratio was 1/2. First term turns out to be 3. If you plug in a 1 for n, 1 subtract 1 is 0. 1/2 to the 0 power is 1. 1 times 3 is 3. So we have 3 divided by 1 minus 1/2, which is 3 divided by 1/2, which is 6. Okay, last problem. Number 16 is from section 8.6. Expand this binomial completely. Now, there were two ways to get the coefficients of this expansion. If you're remembering the discussion from 8.6, one of them was using the binomial coefficient formula, which had all of those factorial. The other way is to use Pascal's triangle. So if it's raised to the 0 power, the coefficient is 1. If it's raised to the first power, we have 1 and 1. Raised to the second power is 1, 2, 1. Raised to the third power is 1, 3, 3, 1. Raised to the fourth power is 1, 4, 6, 4, 1. So these are going to be the coefficients we're going to use. So the first term is going to be this with that coefficient raised to the fourth power. So the coefficient is 1, and then we have our first term 4a raised to the fourth power. Now the next term has this as a coefficient, 4, and then it has our first term 4a raised to the third power, but then it has our next term, negative 3b, raised to the first power. So the first term here, 4a, is raised to the third power. The second term is raised to the first power. 3 plus 1 is 4. The next term has this as a coefficient, 6. And then our first term, 4a, is raised to the second power. And our second term, negative 3b, is raised to the second power. Then we have the next coefficient is 4. And then our first term, 4a, this time is raised to the first power, and our second term, negative 3b, is raised to the third power. And finally, we have a coefficient of 1. And then our last term, negative 3b, is raised to the fourth power. Okay, we simplify. 4a to the fourth power is 4a times 4a times 4a times 4a. 4 times 4 times 4 times 4 is 256. A to the fourth. Now, the next term, 4a raised to the third power. This is 64a cubed. And then 64 times 4, and then that's going to be multiplied by negative 3. So we have 64 times 4 times negative 3 which is negative 768. And then we have the a is going to be raised to the third power. And then b is raised to the first power. All right, the next term, we have 4a raised to the second power. So that's 4a times 4a, which is 16a squared. So this becomes a 16. Here we have negative 3b to the second power. Well, negative 3b times negative 3b is 9b squared, so we have 9 times 16 times 6, which is positive 864. And then a is squared and b is squared. Now, here we have 4a to the first power, so that just stays a 4. Negative 3b to the third power, the negative 3 to the third becomes negative 27, so we have negative 27 times 4 times 4, which is negative 432, a to the first power, b to the third power. And finally, this last term here, negative 3b raised to the fourth power. Negative 3 to the fourth power is 81, positive 81. And then b to the fourth. And that is the expansion.